All right, so then to continue with Einstein, because we're going to talk about his theories and how they go beyond the theories of Newton. In a very famous speech, Einstein apologizes to Newton because, of course, as soon as Einstein came out with his theory, the New York Times said, Einstein proves Newton wrong, Newton was wrong. And of course, that's not true, again, from this picture of, taking a wider and wider view. So he apologizes and he says, Newton, forgive me. You found the only way which in your age was just about possible for a man of highest thought and creative power. The concepts which you created are even today still guiding our thinking and our physics, although we now know that they will have to be replaced by others farther removed from the sphere of immediate experience if we aim at a profounder understanding. So that's what we're going to try to cover today, concepts that are farther removed from our sphere of experience. So just to review this, if the person was in free fall, his weight is 0, okay? And if the person is going in a satellite around the Earth, his weight is also 0. Because both of these cases are acceleration towards the center of the Earth with acceleration value g. Both cases are the same. The only difference between these two cases is that in one case you have no horizontal velocity, and in this case you have a lot of horizontal velocity, so that you make a circular path instead of a straight path down. That's the only difference. The acceleration is the same. All right. So that's all pretty simple, a little bit insightful about the fact that you're weightless and why you're weightless. But now we come to the, what do you say, when philosophers and scientists like Einstein and Newton, from a simple experiment, they reach a grand conclusion. Okay? And the grand conclusion is that acceleration cancels the effect of gravity. Okay? So that's the first part of the understanding. Now comes the next part of the understanding. And this is now all Einstein, okay? He says, suppose that you are in free space, okay? And suppose that in free space you are on a rocket and there's no planet or anything, okay? So there's no gravity, and you're on a rocket and you fire the rockets and the rocket accelerates up, and you arrange your rockets to accelerate so that you accelerate at g, okay, 9.8 meters per second squared. And now suppose you conduct an experiment while you're inside the accelerating rocket where you drop two masses, okay? One mass is mass m and the other mass is twice the mass, okay, double the mass. And you let these two masses go, right? Now the masses are kind of in free space. They're not going anywhere, okay? But the floor of the elevator is coming at them in full acceleration g. So if this person cannot look out the window, she thinks that the two balls are falling to the floor with acceleration g. Okay? And so to this person inside the elevator, crucial point, both masses, m and 2m, appear to fall with the same acceleration g. Right? Remember this big puzzle we had, right, before. Why do all masses fall with the same acceleration? Well, if what we had is a spaceship falling up, it would behave that way, because the floor of the capsule accelerates towards the balls. Okay? So that's the important point, is that in the absence of an Earth-like mass, you can produce gravity-like effects by having acceleration. So now remember the previous conclusion. And this gravity-like effect is that acceleration is independent of mass. And it's a more elegant statement than Newton's, and we'll talk about that some more. But so what we've seen now is that acceleration cancels gravity. And now we're seeing that acceleration in free space, in the other direction, produces gravity-like effects. So that, if for example, there was no Earth, and Einstein was inside this rocket ship, and it was accelerating at acceleration g, then his weight would also read his normal weight. So he would no longer be weightless, because he's accelerating upwards. So the weight will be the reading on the scale. His weight will be the reading on the scale. And objects will fall to the floor with the same acceleration independent of mass. Okay? And so what Einstein then concludes from this two observations, this mental observations, comes to this great leap of thought that acceleration and gravity are the same thing. Okay? Gravity and acceleration are equivalent, which he calls the equivalence principle, and he calls this my happiest intellectual moment. Okay? When he realized that what gravity is acceleration. That's all. This is completely equivalent. So if he was on top of Earth and he did the experiment, he would get the fall like this. But there was no Earth and he was in a spaceship and the spaceship was accelerating, the ball would fall with the same speed versus time pattern as if it was on Earth. So acceleration causes gravity-like effects and gravity causes acceleration. So then he gets to this wonderful conclusion that acceleration and gravity are the same thing. Okay? So what we are seeing here are now advancing views of gravity all the way from Aristotle, who said that gravity makes everything go to the center of the universe, and that's why the Earth is a sphere, and so on. But then he screwed up when he said that the heavier an object, the more it will accelerate to the Earth, right? And then Galileo showed him that no, they will both arrive to the ground at the same time, and so the acceleration is the same. And then Newton thought about why that's the case, and he came up with the idea that if you have a big apple, the Earth pulls on it harder than it pulls on a smaller apple. So that for the force of gravity is proportional to the mass of the apple. It's really a complicated explanation, okay, for Galileo's discovery that if the force of gravity increases with the mass of the apple, then the acceleration will be the same. All right. So the reason why acceleration due to gravity is independent of mass, according to Aristotle, well, that's wrong. And Galileo says, I observed it, and that's the end of the story. Okay? And Newton said, yes, but the reason you observed that is because the force of gravity increases with the mass of the apple. Strange behavior. And Einstein says, no strange behavior. Gravity and acceleration are the same thing. Okay? And so if I'm in the elevator, okay, you could be accelerating upwards with the g, and you would say Einstein's gravity. All right. So we've explained now what gravity is. So now you can see also that Einstein's idea of mass intellectually very different from Newton's idea of mass. Okay? So let draw you the distinction. All right. Newton offered a very complex explanation of mass. And as you know from what we said very, very early in the game, is that the more complexity that you offer in an explanation, the less likely it is that you're close to the truth. Okay? So you'll see now that Einstein offered an explanation of mass which is much, much simpler than Newton's explanation. Newton's explanation had three components to what mass is. So first of all, he says there are two kinds of mass. One is called inertial mass and one is called gravitational mass. And I'll explain to you what this is. I've already done so, but I'm now giving it names. Inertial mass, let's call it mass of I, is the mass that you use in his famous second law equation, force equals ma. Okay? It's the mass that resists the change in acceleration, the change in motion. That's what inertial mass means, mass that's involved in resisting this change in the state of motion. And gravitational mass, according to Newton, is that mass which makes the gravity force larger. You know, if you've got a bigger apple, its gravity mass goes up. But then Newton said that the gravity mass and the inertial mass are equal to each other. Okay? So that's why you get the acceleration to be the same for all objects, because these two are true. So you see he has three components to this whole concept of mass. And Einstein says, forget all that. There's only one kind of mass. Okay? There's only one kind of mass, inertial mass. There's no gravitational mass. I don't need it. Okay? Because I don't need gravity. All I need is acceleration. If you've got some acceleration, I can produce gravity. Then you can say, okay, that's all fine and dandy. You just came up with new words for everything, okay? And you came up with a nice different explanation. But as you know, if you come up with a new theory, okay, you tend to believe that this theory is taking you closer to the truth or taking you further in your understanding if the theory offers you some new consequences, okay? And what you're going to see now is that this simple picture of acceleration equals gravity brings Einstein to a fantastic conclusion. Okay? And the fantastic conclusion is that light must bend in gravity. Okay, now we'll see how he gets that. So he says, suppose you are on an elevator and you're accelerating, and you have a laser, what is this, pointer? You have a laser pointer, and you flash the laser pointer. Then if the elevator was stationary, the beam would hit the opposite side exactly the same height from the floor as it launched. Okay, so these two heights would be equal. However, if your rocket ship is accelerating, then this wall is moving upwards while the beam is traveling across, right? Which means that the beam will not hit exactly opposite, it will hit slightly below, because the time that it took the beam to go across, the elevator has gone up a little bit. So that means that if you accelerate, the path of the light beam will bend inside the rocket, right? So if you're sitting in this rocket, and the rocket accelerates and you shoot this laser beam, it's not going to hit the opposite wall, it's going to hit a bit lower, which means to say it took a parabolic path down. Okay, that's all makes sense for acceleration. But now if you apply Einstein's equivalence principle, that acceleration equals gravity, then the answer is, suppose we are not accelerating in a rocket. Suppose we are sitting in an experimental room on top of a massive planet. Now we know that the massive planet behaves like acceleration, and so this light beam, as it goes across, will accelerate and will bend. And therefore, mass or gravity should bend light. Okay, big conclusion. Nobody had thought that gravity can bend light, and Einstein predicted that. Oh, just paper and pencil, yeah. He just predicts that, and he says, if you have a star out there, and you look for the position of the star exactly when the star is aligned with the sun, then the ray of light coming from the star will bend, because the sun is a massive body, and arrive at Earth on a bent trajectory, and you will think on Earth that this ray of light is coming from a star which is a little bit higher, right? Because normally you think that light travels in straight lines. So your apparent position of the star will be up there. And so he's predicted. Now the problem is, if you try to find this situation, go look at a star in front of the sun. Not possible, right? If the sun is going to wash out the star. But during a total solar eclipse, the moon will come and block the light of the sun, so that you can see the position of the star exactly in totality, right? So he says to everybody, wait for your next total solar eclipse, go measure the position of all the stars during the total solar eclipse, and compare that to the position of the stars when there's no solar eclipse, okay? Say relative to some stars that are far away. And they did that, okay? And when they did that, they found that the shift is exactly what Einstein then modified his theory a bit more, and it's exactly what Einstein had predicted, okay? So Einstein predicted that gravity should bend light, and the observers went and found it, okay? So there we are, the famous experiment. Again, Einstein makes the New York Times and so on, and the genius predicts the bending of light and so on. There's lots of wonderful stories about that eclipse sighting. So the extrapolation of this effect is kind of fun to do. So suppose you are on Earth now, right? And you're looking at this nice castle, right? And you stick in front of this castle a point mass whose mass is equivalent to the mass of the sun, or Saturn, mass of Saturn. Well, this is what will happen to all the light that comes to you from this object. Yeah? So this object will look like this if you're looking at it behind a mass, the mass of Saturn. I'm exaggerating, okay, what we can actually do. But the universe does this for us, okay? And here's how the universe does this for us. And this is now going to turn out to be a very, very important basis of the new discovery of dark matter, okay? Okay, so here's a simple thing. Suppose you have a faraway star, or a quasar, further than a galaxy, a very massive galaxy. And the light is coming from that star, but it has to go past the galaxy to come to you. And you know that the galaxy has a tremendous mass, and so the light is actually going to bend and arrive at Earth distorted. So this object will act like a lens, okay? And because it acts like a lens, instead of seeing one distant quasar, you're going to see two or even more distant quasars, okay? And this is in fact what's been observed with Hubble Space Telescope images, is multiple images of the same galaxy or multiple images of the same star. And so a nice illustration of this is that if you have a single galaxy and the light is coming from that single galaxy towards you through a very massive cluster of galaxies, then this light will bend and this galaxy cluster will act like a convex lens. Okay? And now instead of seeing one galaxy, you're going to see a ring of galaxies around. Okay, because this light looks like it's coming from here, and this light looks like it's coming from here. So this galaxy image is here, and this galaxy image is there. And similar things happen all the way around. And so instead of looking at one galaxy, you'll see a ring of galaxies. All right. Now, okay, suppose you look at this galaxy, which looks like a bunch of rings, and that light is coming through a cluster of galaxies. Then from the bending of light and Einstein's equation of how the amount of bending is related to the amount of mass, from Einstein's equations, I can get a measure of the mass of the cluster of galaxies. I have an independent estimate of what the amount of mass is, and lo and behold, this is an actual picture now of a ring of galaxies that are going through a cluster of galaxies. And this exercise tells you that the mass of the cluster, again, is 6 times the mass of the stars and gas in these galaxies. That there's something else in here besides the mass of the stars, and that something else is dark matter. Let me just point out to you that if you take the results from the Hubble Space Telescope, where you're looking at the dark matter and figuring it out with computers from the light bending and from the movement of the galaxies, and you generate an image, then you see that you can actually find the distribution of the mass over this region, and each one of these spikes is the mass of the galaxy in terms of the number of stars in the galaxy. Okay? But this huge piece of cake, okay, this is like raisins on the cake, right? That's our galaxies. But the bread of the cake, okay, the dough of the cake is our dark matter, okay? And that dark matter is invisible, but we know what its mass is and we know what its distribution is like. And it turns out it makes up nearly 10 times the amount of matter in the galaxies. Okay, I said 6 times before, but if you really do it carefully, it's more like 10 times. So the dark matter, by the way, is the key to the formation of galaxies. Now, we don't know what the hell it is, okay? And it turns out that in terms of the mass of the universe, the dark matter makes up more mass than the regular matter. Okay? And we don't know what it is. So here you can see there's a big quest to figure out what is dark matter. So now I come back to gravity. So Einstein explained that acceleration and gravity are equivalent. But he didn't explain why mass causes acceleration, right? Why does the presence of mass cause gravity, cause acceleration? He didn't explain that. And this then is his explanation. He went through a lot of mathematical efforts to do this, and I'm going to do it by wave of hand, okay? What he showed is that mass causes a curvature in space-time. I'm going to have to explain to you what space-time is, okay? Now, to give you a brief definition, you know what space is, and you know what time is, right? What we are doing now is we're talking about a mixing of the two, okay? The mixing of the two is called space-time. Now, why do the two mix? And I'm going to show you why they mix. And in fact, this guy, Minkowski, was Einstein's math teacher, okay? And he actually called Einstein useless when he was studying math under him. But anyway, later on, Einstein showed him that he wasn't useless, and he predicted this behavior. And then he went back to the mathematics of Minkowski. And Minkowski was so impressed. You know, he says, space of itself and time of itself sink into mere shadows. Only a kind of union between them survive. So let me try to explain to you what he meant. And I can do this by a simple analogy with just different dimensions of space. Okay? So suppose I have a FedEx box. Okay? And I take a picture of this FedEx box with my digital camera, and I place my digital camera right in front of one of the faces, then I see a square, right? I see just 2 dimensions. But if I change the angle slightly, okay, so this is the z dimension of the box, here's the y and the x dimension of the box. If I change my angle slightly, I'll see another surface of the square. So as I said before when I was doing special relativity, that what you see of an object depends on your angle, on your perspective. So you only see 2 dimensions from this perspective, but you'll see two different surfaces or 3 dimensions from this perspective. Okay? Or you can take another perspective and see 3 surfaces. Okay? Top, side, and I don't know if you can see bottom if you do it right. Okay? But what I'm trying to say here is that by rotating your perspective or by rotating the box, you can actually see how the coordinates x and y mix together. Okay? So these are 2 independent coordinates, x and y. But if you rotate them, you can see both of them. And this is how the equations go when you mix it together. Now this is perspective from space. But you remember that when we did special relativity, we talked about perspective from different moving frames of reference. Okay? And this is what happens to the box if I look at the box face from 2 different moving frames of reference, not from 2 different angles. Okay? So if I'm looking at it from a moving frame of reference, and I'm not moving, then if I just stand there in front of it, again I see only one face. But if I am moving and I come past the face of this cube and I take a picture while I'm moving, I take a picture of the face of this cube, I'm supposed to be moving at 50% the speed of light, and I'm supposed to be a distance equal to the height away from the tube, okay, from the cube, about the height of the cube. I will not just see this face, I will see part of its side distorted. And if I'm moving faster, I'll see more of its side distorted. And if I'm moving very fast, I'll see this. Now, what am I doing? I'm saying that what I see depends on how fast I move. And so that space and time are linked, like x and y are linked. And so this is the equation that links t and x. And this is what this is, space-time. Okay? Mixture of space and time. All right. So what has that got to do with gravity, right? Now you remember that Einstein changed the meaning of space and time through his special relativity theories. And just to review very quickly, right? The time, the clocks, 2 clocks can actually read different values according to this equation. So moving, this guy is stationary, this guy is moving. This thing and stationary observers read different times. Okay? I'm not going to go through this explanation again, but the clocks are different. And now Einstein says, instead of using a train, let me use an accelerating object. And the most favorite accelerating object is circular motion. So let me take a disk that is rotating, and let me put a clock on the outer part of the disk, and a clock on the center of the disk, and a clock outside. Now, the center of the disk is not moving, agree? Because the disk is spinning. Which means this clock should read the same as the clock outside, which is also not moving. Okay, so these 2 clocks read the same time. However, this clock is accelerating. It's moving very fast and accelerating towards the center. And since, according to special relativity, a moving clock reads a different time, it should read different time. So in other words, an accelerating clock reads a different time, as we know from a special theory of relativity. But now comes the next step. If gravity equals acceleration, gravity should also cause this effect, because gravity is the same as acceleration. Which means if you have stronger gravity, it should slow down the clock. Okay? So if you have, for example, the Earth, and you put a clock on the surface of the Earth and a clock up in the satellite, the clock on the satellite will read different from the clock on the surface of the Earth, because the gravity is different strengths between these 2 places, and gravity equals acceleration, and this is the example for acceleration and motion. So gravity changes time. Okay? Gravity also changes space. Okay? So we know that different observers have different rulers depending on how they're moving, depending on the frame of reference. And the lengths of the rulers are connected by this equation. So now, a question for you. I have a disk which is spinning, okay? And I place 4 rulers on the disk in these positions. And then I place a ruler outside, which is stationary. And the question is, which of these rulers will experience the largest contraction, what you call Einstein or Lorentz contraction, due to the motion? It's a trivial question. But what's the answer? A, B, C, D. Let's see what you get. C, where is C? I don't remember where C is. Ah, C is outside, right, good. C is the guy who's accelerating the most, right, because he's got the highest speed. V is higher, V squared over R is highest, and that's absolutely correct. Okay, so, to summarize, if you have the Earth and you have space, the presence of gravity, which is equal to acceleration, deforms space, Lorentz contraction, because gravity equals acceleration. Similarly, if you have Earth, you have mass, you have gravity, gravity equals acceleration. The presence of acceleration deforms time in this way. In other words, if you have a clock here, it's going to, this clock is going to be slower than this clock. Sorry, this ruler is going to be smaller than this ruler. Okay, I did it the other way. This ruler feels more contraction than that one. Okay, so now comes the big statement. Okay, gravity deforms both space and time. Okay, and this is Einstein's view that if instead of drawing 2 dimensions of space, we draw a dimension of space-time, then what gravity does is it deforms space-time. Okay, and so all of these different masses are sitting in a deformed fabric of space-time. And this guy Wheeler, who also was very involved in the mathematical theory of gravitation, explains Einstein's theory that mass tells space-time how to curve, and mass, the other mass, then moves according to the curved space-time. Okay? And so what gravity really is the motion of mass in curved space-time. Okay? So that's what gravity is according to Einstein. Mass deforms space-time. Objects move through curved space-time, create an illusion of an attractive force, and so gravity is an illusion. Okay? So here you have a simple example. Suppose you have 2 objects on 2 parallel lines. Okay? So here's an object on a parallel line, and here's an object on a parallel line. And these 2 objects are moving in a straight line according to law of Galileo. Okay? So it'll look like these 2 guys are not really attracting each other because they are moving in space, which is really straight. Okay? So because the lines are parallel and the space is straight, these objects will always be the same distance from each other. But now, instead of having straight space, so now suppose I have a curved space and 2 parallel lines. So down here at the equator, these 2 lines of longitude look parallel. Okay? But if I launch 2 objects, 2 ships, okay, from the equator and they move to the pole along the lines of longitude, which are always the same, they come together. So when you have motion in curved space, it appears as if objects are being attracted to each other. And that's what gravity is. Motion in curved space, actually curved space-time, and that gives you the idea of attraction. All right. So gravity is an illusion, and what really happens, if you have a planet like the sun, is it deforms space-time, and light can go around in circles, or planets go around in circles. And I'm sure that, did they keep the black hole demonstration at the Science Center? Did you have that big conical black hole where you can circulate little coins? So this, if you put coins in here, it will make orbits like a planet, and then the orbit goes and they get your coin. Okay? So that's the basic idea of gravity. All right?